and my graph will look like this. It goes back to the same point. Say this was an isotherm, say at temperature T1, and this isotherm is at say at temperature T2. T1 is the temperature of the source and T2 is the temperature of the sink. So point A, the pressure value is PA and the volume value is VA. At point B, say the pressure value is PB, volume is VB. Here it is PC, VC, and here it is PD, VD. Now during this expansion, isothermal expansion, Q1 amount of heat was absorbed by the source. Sorry, not by the source. Q1 amount of heat was absorbed by your working substance. And this process C to D, Q2 amount of heat was liberated. And BC and TA is your adiabatic curves, so obviously there was no heat exchange in these parts. Now according to the first law of thermodynamics, we know dq is du plus pdv. But as you can see here, AB is a curve, is an isothermal curve, and for an ideal gas in an isothermal curve, the change in internal energy is zero. In any isothermal process, the change in internal energy is zero. So I'm left with only dq equals to pdv. So q will be simply integration of pdv. Now using this, I can calculate the expression for u1. So q1 is integration of pdv, volume is expanding, increasing from VA to VB. So let us calculate. VA to VB. Now as we know, for an ideal gas, PV is equal to nRT. Here the number of moles I'm taking 1. So I have this RT by V. RT is constant, so I take it out of integral. I just write integration of 1 by V dV. Now in this process A to B, my temperature was fixed at T1. So let me mention it here. T1. And volume is running from VA to VB. So integration of 1 by x dx is going to be log x, exponential log. So here also I'll get the same thing, log e v. And of course this is a definite integral with lower limits VA and upper limit VB. So I'm going to substitute it, log VB minus log VA RT1. I'm missing it every time, make sure not to miss it, VB by VA. So this is the expression for Q1. Similarly, I can go on to find the expression for Q2. Here the volume is running from VC to VD and the temperature is constant at T2. So let's calculate by similar steps. I'll get this. Q2 is equal to RT2 1 by V dV. The volume is running from VC to VD, and of course Q2 is the amount of heat rejected by the working substance. So I'm going to add this minus here. So I'll get minus R T2 log E VD by VC, which is equal to RT2 log E VC by VD. So here I have arrived at the expression of Q2. Now let us further proceed to find the expression for efficiency. As we saw before, it was this 1 minus Q2 by Q1. Let us substitute 1 minus RT1 log E VB by VA, and this is R T2 log E VC by VD. So you can see your R and R is getting cancelled. Now one more interesting thing, as you can see here, that BC is an adiabatic curve, so I can write one relation connecting temperature T1 and volume at this point. I can write an expression. The expression is T1 VB power of gamma minus 1 is T2 VC to the power of gamma minus 1. Similarly, for this adiabatic dA, I can write a similar expression. T2 VD gamma minus 1 equals to T1 VA to gamma minus 1. Okay, let me select it. I did a mess. Anyways, let's remember it. T1 VB gamma minus 1, sorry, T1 VB gamma minus 1 is equal to T2 VC gamma minus 1. Again, T2 VD gamma minus 1 is equal to T1 VA gamma minus 1. Now what I'm going to do here is I will use these two equations to arrive at a formula connecting VB by VA and VC by VD. If you see carefully, from equation 1 I can write this: T1 by T2 is VC by VB to the power of gamma minus 1, and from expression 2 I can write T1 by T2 is VD by VA to the power of gamma minus 1. So indirectly I have proven VC by VB is equal to VD by VA, which also I can write as VA by VB is equal to VD by VC. VA by VB equals to VD by VC, or VB by VA is VC by VD. So as you can see, using this I can say this and this are equal, and so they are getting cancelled. So the efficiency of eta is reduced to 1 minus T1 by T2. So here there is an interesting result. We have proven that the efficiency of an Carnot's engine depends only on the temperature of the source and the sink, and it is independent of the working substance. Thank you for watching. Have a nice day. See you next time.